In this video, we continue with the Computer Science AS level curriculum course code 9618, talking about topic 4.2, assembly language, assemblers, and addressing. Let's go ahead and take a look at the learning targets. So candidates should be able to. They want you to show an understanding of the relationship between assembly language and machine code. We're going to talk about both of those. We're going to describe the different stages of the assembly process for a two-pass assembler. We are not going to trace a given simple assembly language program. That's a whole nother video, so that is the next video that we're going to be posting. We need to show an understanding that a set of instructions are grouped, including data movement, input and output of data, arithmetic operations, unconditional and conditional instructions, and comparing instructions. That may sound overwhelming. We have broken each of these down into its own slide to make it as easy as possible for you to understand. And then the modes of addressing, including immediate, direct, indirect, indexed, and relative. Now for the modes of addressing, that's really going to come along when we do a trace table. You'll be able to see it. It's one thing to talk about it, it's another thing to actually do it and understand it. But let's go ahead and let's get started. So assembly language and machine code. Now the only language a CPU can understand is machine code, a bunch of zeros and ones. Every different type of computer chip has its own set of machine code instructions. A program stored in main memory is just machine code that the CPU can run automatically during the fetch execute cycle. Now, when we're talking about the main memory, we're talking about the RAM. Main memory is not the hard drive. Your hard drive is secondary memory. Now, each instruction in machine code performs one simple task like storing a value in a memory location at a specific address on the RAM. Machine code is written in ones and zeros, which can crowd the screen very quickly. Now, sometimes it's displayed as hexadecimal, so human programmers can understand it a little more easily. Writing machine code is tedious, it's time-consuming, and it's likely to have errors. If you're writing a bunch of zeros and ones, trying to remember what the combination of zeros and ones do, it's almost impossible, and you're going to run into errors. The only way to test it back in the day was to write machine code, run it, and see what happens. And most of the time, it didn't do what they wanted it to do. Eventually, other programming languages were developed where instructions are easier to learn and understand. VB.NET, Python, Java, C++. But we also have assembly language. So a program not written in machine code has to be translated before the CPU can carry out the instructions, and this is why language translators were developed. So we're going to look at machine code with assembly language and see the benefits of why assembly language is used. So here we have some machine code. We have an opcode here. Notice we have a mnemonic, which is an abbreviation of words, and then we have the opcode in binary, which is your machine code. So let's take a look at INC. So INC stands for increment. It's much more easy for me to remember that the increment code in assembly language is INC rather than trying to remember that the machine code is 00000011. Looking at all these, there's no way I would memorize this. And this is a very small set of instructions here. Trying to memorize all those instructions, that would be a nightmare. If I want to store something, it's much easier for me to remember STO rather than 00010000. And if I'm typing out machine code, a bunch of zeros and ones, I could easily mistype a 0 or 1, and now my program's doing crazy things that I didn't want it to do. So assembly language. Well, what is it? So it has an opcode, which is an abbreviation for the operation code. It has an operand, which is a character or an address. And it has a mnemonic like add for addition, INC for increment, DEC for decrement, decreasing by 1, LDI for indirect addressing. So here we have add number 45. I could give this to any human, and they're saying, well, you probably want to add. What do you want to add? We want to add the number 45. So the opcode is the operation and the addressing mode. The addressing mode is not the address 45, but rather the number 45. That's what that pound sign means. Now, if I was to put this into machine code, I would not have this machine instruction, I would not have the opcode add. I'd have to memorize whatever that is, then the address mode, and then whatever this code does, which is part of the operand, which is a character or address. Just so you know, these two do not match up. These are not the same thing. This is just an example. Looking at this machine code, I have no idea what this does. I have no idea what this does at all because I don't have those codes memorized. I am much more likely to remember add number 45 than whatever this does, or trying to memorize what the add instruction is. So that's what assembly language is. It makes it easier for us to understand what the CPU is going to do. Now, assembly language was the first language to be developed, and is closely related to machine code and uses mnemonics instead of binary code. To add the contents of address 20 to the accumulator, we would do the following. Now, in machine code, the instruction is this. I looked it up and was able to find the machine code. There is no way I could give this to any programmer and say, please tell me what this does. They're going to tell you it's some form of binary and it does something. But if we wanted to add 20 to the accumulator, we'd have to write this out in binary. That's not going to transpire at all. For the assembly language instruction, we simply do this. Add 20. That is so much easier to understand. Now, in case you are wondering how to add a number, you would write add number 20. An assembler translates the source code, which is the assembly language, into machine code for us. So if we want to add the number 20, we have to use this number sign. If we have just add to 0, that would be add address 20, which we'll talk about later. So with assembly language, you have what's called an assembler. The assembler translates each assembly language instruction, like add, subtract, increment, decrement, into machine code instruction. And it also checks the syntax. It looks for opcodes from the appropriate machine code instruction set are used. Are you using things that don't exist? If so, it's not going to allow you to do that. The things that do exist, are you using them correctly? That's what we mean by checking the syntax. Now, because errors are identified during translation before the program is executed, it speeds up development time. And there are two types of assemblers. There's a single pass assembler and there's a two pass assembler. Now, before we discuss a single pass assembler, we need to take a look at a symbol table, because the symbol table they're going to talk about. This is a symbol table. So there are two things we have here. This may not make a lot of sense, but as we go through the assemblers and talk about them, it'll make more sense. So this symbol table, this on the left side here, are variables that the program may or may not recognize. We have total, we have average, we have pay rate, and we have date. Those are things that appear inside the assembly language program, whatever it may be doing. Now over here on the right hand side, you have the address. So if we're looking for total, the computer doesn't care what's here. It does care where that information is stored. So if I wanted to update total, I would need to access address 100. If we want to update pay rate, I don't need to get the pay rate. I need to know where on the RAM the address that it's stored in, which is 2031 or 2031. So this is a symbol table. We take words, we put them somewhere on the RAM, and we have an address of where it is stored on that RAM. So let's talk about the single pass assembler. It takes the machine code instructions, puts it directly into the computer memory to be executed. Now the problem is what we call forward references. For example, if the assembler is on line 325, and we have JMP 500, and JMP means jump to line 500, it doesn't know how far away that is, nor what is written on line 500, because it hasn't gotten to it yet. If the assembler encounters an undefined label, it puts it into a symbol table. Well, the address where the undefined symbol's value has to be placed when the symbol is found, and also placed into the symbol table. At the end, if there are any more undefined labels still in the undefined state, then the assembler errors out. It won't run. Now, what about variables I created? What about ones we create? Well, it needs to be able to define these labels or cannot be used. The advantage of a one-pass assembler is that's fast. It runs once and goes. It's known as a load and go. So let's take a look at one of those forward references. We said forward reference is a problem. Let's talk about what that means. So below, this code is run, and I'll show you what the code looks like. The computer will not know what found is because it hasn't arrived at that line yet. Remember, A single pass assembler translates each line of assembly language into machine code one instruction at a time. So here we have load 200, CMP, number 0, JPN, found, JPE, not found. If it's not equal, and we'll talk about what this JP and JPE is, don't get overwhelmed by it. Super easy, we'll get to it. But basically what this is we're going to load address 200, we're going to pair it to the number 0. If they are not equal, we jump to label found. Well, when the computer runs this, it doesn't know where found is, so it can't even jump to it. And then if it says they are equal, jump to not found. That's not a problem if they're equal, because we know what not found is, but the computer has no idea where found is. That's what we mean by a forward reference problem. So found, we don't know what happens there. We know it outputs because we can see it, but when the computer does it one line at a time, it has no idea where found is, it doesn't know where it's stored, and it doesn't know what happens. All right, the two-pass assembler. It overcomes the single-pass problems. It produces an object code program in machine code that can be stored, loaded, and then executed at a later stage. Now, this requires another program called a loader. Two-pass assemblers scan the source code twice so they can replace labels in the assembly program with memory addresses in the machine code program. Now, when we talk about object code, we're talking about a computer program after translation into machine code. And that brings us back to the symbol table. In a two-pass assembler, we have the symbols and we have the addresses of where they are. So let's talk about the passes that happen, because this doesn't happen all at one time. There's two passes in the two-pass assembler. In pass 1, we read the assembly language program one line at a time. Step 2 in pass 1 is we ignore anything not required, like comments. Comments, white space, all of that is taken out. Then we allocate a memory address for the line of code that we are on. We check the opcode, make sure it's in the instruction set, make sure we're using opcodes that actually exist, and then we add any new labels to the symbol table with the address if it is known. We place the address of labeled instruction into the symbol table. Now, after the above steps are completed, the second pass takes place. So here, we have this happening in pass 1, and then we get to pass 2. We read the assembly language program one line at a time. We generate object code, including the opcode and the operand from the symbol table made during pass 1. So when we're looking at that symbol table, we know what the opcode is, we know what we're performing it on, and we know where it is stored. Symbolic addresses become absolute addresses. We know where on the RAM they're exactly stored. We save or we execute the program. Now, object code is the code after being translated into machine code. You want to remember that. All right, let's keep going. Getting into the data movement instructions. So this can be a little overwhelming, but it's not too bad. Like anything, it just takes some practice getting familiar with it. Now, data is stored at one location, which is copied into the accumulator. It can then be stored at another location. It can be used in a calculation or even used for comparison or output. So let's take a look at the various different data movement instructions we have. So your professor or teacher will probably give you a sheet like this. If you're in Cambridge, you need to be very familiar with these. You don't have to memorize them, but one of the biggest mistakes you can make is saying, oh, well, I'll get a reference sheet on the exam. I'll be able to figure it out. I really need to encourage you to be familiar with it. The more familiar you are with it, the more confident you'll be in that high stress environment, and the better you'll be able to do. So we have LDM. This is immediate addressing. We load the number in to the accumulator, and we have a bunch more of these. Here we have store again. We have LDX, index addressing. Form the address from the address plus the contents of the index register. We're going to do all this in another video, so it makes a lot more sense. But we need to talk about these data movement instructions and how they work. So let's get into input and output of data instructions. So here we don't have input and output, but it will show up. There's no opcode is required here. A single character is input to the accumulator, or its output from the accumulator. These instructions allow data to be read from the keyboard, or we can output it to the screen. What is the mnemonic, it is IN for input, OUT for output. So if we see IN, we're going to key in a character and store its ASCII code value in the accumulator. If we use OUT for output, we output to the screen the character whose ASCII code value is stored in the accumulator. So if we had OUT 65, that would output the capital A because the ASCII code value of capital A is 65. And like I said, we'll look more at that trace table in a upcoming video. So arithmetic instructions. We can perform simple calculations on data stored in the accumulator. Once the calculation is done, it is stored in the accumulator, overwriting what was there. If you want to store what was in the accumulator, you're going to have to store that. If we perform a simple calculation, we're going to overwrite what's in the accumulator. So we have add. We can add an address, the contents of an address. So if I add 200, that would add address, whatever stored in address 200. Add number in. So if I had add number 200, that would actually add the value of 200. Same thing with subtract. Then we have increment, which is add 1 to the contents of the accumulator or the index register. That's what IX is. And then we have DEC, which is decrement, subtract 1 from the contents of the register. So these are your various arithmetic instructions. We also have conditional instructions. So jump changes the program counter to the address specified. This means it's not necessarily the next line that is executed. We could jump over several lines of code. It's often used with compare instructions. So you're going to see jump most of the time when you see the compare instructions. We have JMP, which is jump to the given address. There is no compare instructions here. You're literally jumping to whatever address is written. JPE, following a compare instruction, you're only going to jump to the address if the compare was true. So you got to look for that CMP code. We're comparing it to that number. If it's equal, we're going to jump to the address. And then the JPN means if it's not equal, meaning if the compare was false. We also have the compare instructions. The contents of the accumulator is what is compared. It's often used with the jump instructions that we just went over. So we have CMP address. We're comparing the contents of the accumulator with the contents of the address. We can also use CMP, the number sign in, which literally means compare the contents of accumulator with a number. And then we have CMI, which is indirect addressing. The address to be used is at the given address. Compare the contents of the accumulator with the contents of this second address. So if this is CMI 300, that means you go to address 300 and stored at address 300 is the address that you need to go to compare those values. And like I said, this is why it's so important you become familiar with this, because that you can be very overwhelmed in the test. And we are going to make a video that walks through a trace table so you can feel extremely confident. And we'll be walking through a few. So let's talk about the modes of addressing. Like I said, we'll see this in the trace table. It is not enough just to watch this video and not do a trace table, but we don't want the video to be exceptionally long. We want to get our information, so when we do our trace table, we have some background knowledge. So we have absolute addressing. The contents of the memory location in the operand are used. If the memory location, address 200, had the value 20, then LDD would load 20 into the accumulator because it is the contents of the memory location. Not the address, but the contents of that address. We also have direct addressing. The content of the memory location in the operand are used. So if the memory location, address 200, had the value 20, then we would do LDD. We would load 20 into the accumulator. So doesn't that say the same thing? Well, yeah, it does. Absolute and direct addressing mean the same thing because they are the same thing. So if you're like, oh my God, what's the difference? There isn't a difference. They are the same thing. Sometimes they talk about absolute addressing. Sometimes they talk about direct addressing. You just need to remember that they are the same thing. So indirect addressing. So indirect addressing does come up, and it's one of Cambridge's favorite to use. The contents of the memory location in the operand are used. So if the memory location address 200 had the value 20, then what we would do is we would go to address 20, and whatever value was there, that's what we would store in the accumulator. So you go to the address, and then it tells you what address to go to. So you're going to 2 addresses. Then we have indexed addressing. The contents of the memory location are found by adding the contents of the index register. Most of the time it's used IX. I have seen once when they used IR, but IX is commonly used. So what we do is we add the contents of the index register to the address of the memory location, and the contents of that is used. And you're going to see that in a trace table. It's very hard to explain without seeing that as a trace table. But if you just go to the trace table and say index addressing, what is that? You may not have the background knowledge, so maybe overwhelmed. So this, with the combination of a trace table video, which we're going to make, will definitely help you out. I want to see everybody succeed. Immediate addressing. The value of the operand only is used. For example, if we had LDM number 20, we're not going to address 20. We're using immediate addressing. We're adding 20 into the accumulator. And the last one we have here is relative addressing. The memory address used is the current memory address added to the operand. So if we had JMR number 5, this transfers control to instruction 5 locations after the current instruction. And what that means is we are jumping 5 lines. Hope you guys found this video helpful, building this background knowledge so we can do trace tables. If you have any questions, please post a comment below. If you found this video helpful, give it a thumbs up and subscribe to help the channel grow. We'll see you guys in the next video.